Welcome everybody. Today we have the pleasure to listen to Professor Nardini's talk. He's part of the LISA collaboration, and he's now a professor at the University of Stavanger. And in the past he has been, he had worked with Mariano Quiroz, and he held various postdoc positions, including one in Helsinki, dedi. And yeah, we are excited to hear some hot news from Lisa. Please start.
Okay. Good afternoon, good morning, everybody. Many thanks for the invitation. So today I would like to briefly cover the science that Lisa can make. So I will put more emphasis on the stochastic backgrounds and a bit on strong first-order phase transitions. But first, let me give a general overview of the topic. By the way, if you have questions, please interrupt me whenever you want. So currently, if we focus on this frequency range, we have two main techniques to measure gravitational waves. One at the nanohertz is the method consists in observing pulsars, and you have the so-called pulsar timing arrays. What you do in this case is that you keep monitoring different pulsars, you compare the signals that you receive from them, and in case of unexpected delays of one signal with respect to the others, in this case you can interpret the signal with as a signal of gravitational waves. So by measuring pulsars, you are sensitive to gravitational waves in the nanohertz. The other method we have is to do interferometry, and this is LIGO style. You have an interferometer that has here a 90 degrees between the two arms, and the lengths of the arms are around order 1 kilometer but order 1. And this experiment, and also future experiment like Einstein telescope, where the arms will be a bit longer, are sensitive to gravitational waves in the, let's say, between hertz and kilohertz. Okay, but here in the middle, what do we have? Well, currently we have nothing, and of course there is a lot of science in this frequency range. In order to measure gravitational waves in this frequency range, what you can do is to use the idea of LIGO, which is interferometry with arms of the order of 1 kilometer, and extend these arms to million kilometers. And so in order to do a million kilometers, of course, you need to go to space. And this experiment is LISA. The idea of LISA is can be roughly sketched in this way. You take two LIGO detectors, which, as I said, they have the arms that are separated by an angle of 90 degrees. You squeeze it to 60s, and you do the same also with the other interferometer, and you squeeze it in such a way that this angle is 60 degrees, this angle is 60 degrees, so this one is 60 degrees. And in this way, you obtain two LIGO detectors that are joined with they have a common arm. So notice that you can, in this way, you can measure the signals in different way by different interferometry, by using different sides of the triangle. But in the end, the two completely independent, linear dependent measurements are those of two interferometers. You can combine the thing as you want, but in the end, two. Even if in principle, you can combine them in three. So you can have, for instance, this interferometer, this interferometer, and this interferometer. Three. But one of the three is a linear combination of the others. So as I said, in order to be able to measure gravitational waves in the millihertz, you need arms that are very long. So in the case of LISA, we are speaking about arms that are 2.5 million kilometers. And what you need to do is to replace the mirrors of LIGO by masses that are in free fall. These masses in free fall are the extrema of the vertices of the triangle. And what you do is, by doing very accurate interferometry, you measure the relative displacement of these masses in free fall. Where do you locate these masses in free fall? Well, in the case of LISA, you locate them along the Earth orbit. LISA follows Earth along its orbit, which means that also it's pointing towards different directions along the year. And exactly as the idea of LIGO, if you measure a relative displacement of the masses, well, this is a signature of gravitational waves. In LISA, is planned to fly to take data for at least 4 years. This implies more than 4 years, because because in LISA there are periods every 10 days roughly, where you have to stop the experiment and point the antenna towards Earth and transmit data. So during this period, of course, you're moving the antenna, you're making a lot of noise, so you're unable to take measurement during this time. So the plan for LISA is then to have 4 years of mission divided by the duty cycle of LISA, which is roughly 0.9%, 90%. But as many experiments, when you build an experiment to go to space for some years, you put some margins, and it often happens that the experiments can take data for longer than planned. So in the case of LISA, what you need is to put some fuel in the microthrusters. So what will be done for LISA is to have fuel and consumables for 10 years. But still, the engineers are building experiments with margins, planned to adopt it for a 4-year divided duty cycle, years of mission. Then the idea of LISA is quite old. It's not something that occurred in the last years. So I'm not so young that in this epoch I was really scientifically active, let's say. And but you can see that the idea of having a kind of LIGO in space starts in the early 80s. You can also see variation of the names and variation of the configuration, but in the end, the idea is let's say the same since the 80s. So basically, you need an experiment that is 1,000,000 kilometers with arm of 1,000,000 kilometers. You need to be in space. You need to have the masses in free fall, and you do interferometry.
And this Lagos was never set up, or it was just a
Oh
project?
no, these are different proposals. I mean, the point of the idea of it's a while that the community is trying to propose a LISA-like mission, and this started and each time you propose a mission, also you change a bit the name, as you can see here, or a bit the design, but these experiments were never launched. These were basically the prototype proposals of LISA. Okay. So all this, what was learned by these proposals, converge into LISA. You can say that already in the end of the previous century, the name was fixed as LISA. But I guess that for in our nowadays perspective, what matters is what happened in the late, let's say, 10 years. So what is particularly lucky for us was that in 2013, the European Space Agency decided, also due to the pressure of all the previous proposals, that it was worth having an experiment focusing on the gravitational waves universe. This was the topic of the mission. L3 means for large. So it's the European Space Agency missions are divided by also by prices, and L3 means the expensive ones. So in 2013, there was the decision that at some point in some years, we will have a call for an experiment that covers the topic, the gravitational wave universe. Then 3 years later, there were 2 important results. One is the direct detection of gravitational waves by LIGO. And this, of course, was really important because it was a very practical proof and that it's possible to measure gravitational waves, and gravitational wave science is exciting, not only for a niche of community, but also for the general public. And then there was there were the results from the ELISA Pathfinder. So the results were very, very important. And so let me mention briefly the ELISA Pathfinder. So what would you like to do for an ideal ELISA experiment, an ideal interferometry in space? Well, conceptually, the requirement, the idea is that you want to, in an ideal case, you want to put masses in perfect free fall, ideally, okay? Then what you want to do, you put these masses, okay? Whatever. I mean, the configuration doesn't matter, but the point is that you need masses in free fall, and then you have to perform to be able to measure the relative displacement of these masses that are in free fall. So the method is interferometry, but even in an ideal experiment, I mean, you have to be a bit realistic, and the fact that you are making measurements of the position of this the relative displacement means that, for instance, you have the noise that is touching the masses. This implies a shot noise, and this shot noise is a perturbation of the free fall assumption. So, of course, you can, since you are making measurements of these masses, you are unable to really put them in free fall. But in ideal case, you are able to know exactly the perturbations that you put on the masses, you subtract them, and in this way, you still have a perfect measurement of the relative displacement of the masses, taking into account the perturbations that you have introduced. So this is the ideal experiment. But now, in 10 years ago, roughly, the European Space Agency decided that it was important to have a proof of, to prove that there was the technology to build such a plan, at least within the accuracy that were proposed in the experiment. So what kind of test you can perform? What you do, and what was done, was you take conceptually an arm of LISA and you squeeze it. So you take the two masses and you put them close at a distance of 40 centimeters. Everything this will be in space, and since in 40 centimeters you are not able to really put the two masses in free fall, what you really do is you take one that is fixed and the other is in free fall, and you're measuring the relative displacement of these two masses. Basically, since one is fixed in the house, in the cage that is of the satellite, basically you're measuring just the free fall of this mass. And you do interferometry. And what you want to show, to be sure, is that you are able to put this mass in free fall and subtract the perturbation due to the measurements at the accuracy that is required by LISA. Technically, the goal was not LISA, but some order of magnitude worse than LISA. But at least if in this proof test experiment you can achieve such a high accuracy, okay, for sure you will be in a good track for LISA. And this was the result. The requirement by ESA to have a successful, to be sure that we are in good track on what we are proposing for LISA, was to have the accuracy, the residual relative acceleration of the mass below this line. And this was the result, okay? So in some regimes here, you are even below what you expect for LISA. So the result was really important, because it was a proof that we have the technology to have LISA. So,
excuse me, can you explain again, this experiment was done for which separation of the two masses?
40 centimeters.
40 centimeters.
This is the picture.
So
yeah.
Okay, can you explain to people who are not experts why this is relevant for a separation of 1 million kilometers?
No, indeed, you're testing. Yes, sure. I was too fast. Yeah. You're only testing a part of the experiment. In particular, the laser part.
Okay. So it's just a test of a part of the experiment.
Yes, indeed. I mean, here what matters is, you can see, is this region. Okay. I mean, okay. No, forget my last statement that adds only entropy, but it's only to test a part of the experiment. This was related to the lasers, and also in order to interpret these results in view of LISA, you had also to rescale some quantities. Okay, but I guess that people it was considered satisfactory given all the descaling and the fact that you're doing a prototype. It was sufficient to have the noise in this region below this line, and it was successful. Notice that LISA goes also to here on the left, but here, as you can see, there were no restriction on the noise for this particular experiment, the Pathfinder. Okay, exactly because of what I'm saying. It was testing only this part. Okay, did I answer?
Okay, please go on.
Okay. Then we said that in 2016 we have results from LISA Pathfinder, successful, and the results by LIGO, wonderful. Then this, I guess, created an excitement such that the European Space Agency decided, okay, it's time to have the call for the experiment that was announced in 2013. And in 2017, there was different missions that were proposed. And this is the proposal for the Laser Interferometer Space Antenna, LISA. And ESA decided to approve this experiment. So in 2017, I guess there were big-ish news. LISA will be built. It has been approved. Then something that I was not completely aware by an external live from an experiment was what happens once the experiment is approved. And I learned here in these years. So first of all, once the experiment is approved, doesn't mean that all details are approved. You have to prove everything, and if something goes wrong along after the approval, doesn't mean that ESA will be the experiment in any case. So I guess that from my point of view, what I know, right, some milestones. So shortly after the mission was approved, there was a big discussion about whether you need LISA with three arms, or in principle it was 3 arms, so a triangle configuration, or it was enough to have this configuration. So basically all discussion is not much about science, but about budget. And it was decided that it was important to have the 3 arms because this improves the measurements, but not only, also if at some point, for some reason, one of the laser links breaks down, you still have the experiment flying. This okay, a bit worse, but still. So
you before you explained that, so I understood that you have a kind of redundancy.
yeah.
So it means that also having 3 arms allows to check that everything is fine. So
no, I mean, the point of the redundancy is when you have a triangular configuration, because okay, label the vertices A, B, and C. So you can do, you have a LIGO-like experiment in AB, BC, this one. Okay, then you have also AC, CB, and these are the 2, right? And then you have BA, AC, which is this one.
Yeah.
Okay.
But you have
but, sorry?
No, please go on.
No. And then what I mean is that this one, in the end, is a linear combination of the other 2, because they are using common arms, right?
But
it's not completely independent. And so this redundancy is possible only when you have the triangular configuration. When you have 2, it's 2. Okay. So then other topics that were discussed. Okay, the duration of the mission. And it was decided that it's worth having 4 years of mission, but no mission, sorry, of data, which means that we have to evaluate the duty cycle of the mission, and the goal is to have 4 years of data. So, as I said, since we have some time during which LISA cannot take data, actually the duration of the mission is a bit longer than 4 years. Moreover, the LISA sensitivity is covering a broad range of frequency. But of course, to keep the extrema of the sensitivity well under control, you have to be careful, and being careful for industries means money. So there was a big discussion about whether it was really important to have LISA below the 0.1 Hertz. The initial proposal reached 0.01 millihertz. So the decision was that there are no crucial science objectives below 0.1 millihertz. So the experiment will fly. We will make our best to have the sensitivity under control also below the 0.1 millihertz. But there, if something goes wrong, it's, let's say, it's fine. So there is not much pressure on industries to have the sensitivity that is very, very well under control below 0.1 millihertz. And then more recently, right now, there is further activity, because we are going from what is called phase B1 to phase to the next one. And the point is, it is so-called implementation. What does it mean? That now the community, technically is the European Space Agency, with the support of the LISA consortium, is writing a document, big document, that is summarizing the state of the art of the mission. And the focus is not much about science, but all the pipelines. So to prove that we are in a good track to have the pipelines and the methods to achieve the science goals we are proposing. This is typical. This red book is a keyword for all the missions. And if in
Germano,
yeah,
is it this red book is in public domain or?
no, we are writing that, and I
Okay.
guess it's the first time I'm involved in these kind of things. I think that I mean, we are writing that. ESA will submit, will approve, and I think that when everything will be decided, it will be, you know, for sure it will be published. Maybe not under archive, I don't know, but because if you go to other missions that have been approved, on the web page, ESA web page, you find the link to these red books. Okay. So, but now it's not public. Actually, now technically it doesn't exist, and we have to hurry up to write it. The decision will be around spring, and if, and I hope that this if it will be true, the European Space Agency will decide that we are on the good track, and then the European Space Agency, and not only the European, sorry, I'm a bit Eurocentric here. There are other entities. There is also a good fraction of the NASA, and there is also, I don't remember the Japanese one, sorry, the name, but the Japanese National Space Agency, and of course others. But politically speaking, it's the European Space Agency, the main lead, and the entity that takes the main decisions with the support of the other. So what I wanted to say is that here we are starting, if everything goes fine, contracts with industry will start, which means that industries will start building LISA. So this is really, and the launch will be in mid-30s. Okay, then I guess that now we have to move to the science of LISA briefly. And so what kind of sources do you expect in the milliards? Well, you expect many galactic binaries that are made of white dwarfs and with some probability neutron stars and black holes. These are okay, light objects. I mean, white dwarfs and neutron stars. And these kind of sources are since you are when they are in the galaxy, statistically they are still in the spiral phase. So basically they are almost circular. We expect to be almost circular, and basically with a distance that implies that the binary is not evolving much in frequency during the mission. So these are monochromatic sources here. Then we expect to have extragalactic binary black holes, and like of stellar origin or stellar mass. And these are the kind of object that LIGO and CAGRA and Virgo have been measuring. With the difference that, again, here, I mean, this is how they are shown here. Here they're still in this spiral phase, and when they merge, they move away from the LISA band and go into the LIGO Einstein telescope band, the ground-based interferometer band. Then you have also other kind of black holes with supermassive black holes of where binaries are have masses of the order of 10 to the 4, 10 to the 8 solar masses. You have also other configurations. We don't know exactly the populations, I mean, how abundant these objects are. But this kind of object is very interesting because it's an extreme case where you have that the two binaries have a mass ratio that is very large. For instance, you can have an extragalactic, solar mass black hole orbiting around the massive supermassive black hole here. And this kind of object, when they are spinning and they have some large eccentricity, they have a waveform that is very, very peculiar and also numerically hard to evaluate and to predict. And these are, as you can see, are not trivial, and are important to perform tests of GR, because really here is GR, extreme GR calculations. Then this is the kind of astrophysical sources you have in LISA, and with these sources, the main science objectives that you can achieve is to understand the formation and evolution of the astrophysical populations. You may be able to see departures from the standard paradigm, and so in some cases maybe you are detecting also primordial black holes. One way to detect primordial black holes, for instance, is to have black holes at very, very high redshift when stellar formation didn't occur yet.
So,
Then, yeah.
For primordial black holes, which mass range, for which mass range this experiment is sensitive for?
Yeah, it's I don't have the plot, but it's sensitive from, okay, the question is, should be a bit, maybe, I mean, the answer I should specify. The point that you're sent, I don't remember the numbers, but basically you're sensitive to less than 1 solar mass, I mean the white dwarfs region, right, up to 10 to the 8, maybe, I don't remember exactly the number, solar masses. But then you have to, I mean, the point is that you're sensitive, but then it depends at which redshift, right? Because if you are in the tail of the sensitivity, you will be able to measure the numbers that I told you, but maybe you don't have enough sources nearby to measure them, right? Then you have around the peak of sensitivity, where, let's say the peak of sensitivity, I guess it's around 10 to the 5, 10 to the 6. If you want, at the end of the talk, I browse because I know the figure, but I don't remember the numbers. And around these mid masses, you reach the peak. So it's where you have the maximal redshift sensitivity. And having maximal redshift sensitivity in the region means that you have maximal also sensitivity to those masses. Okay? Yeah. And so, concerning if primordial black holes were the things that were triggering the questions, of course, you are sensitive to primordial black holes in all this regime by directing the sources. A different issue is the stochastic background that you can measure from this object, but this is a separate topic. Yes. Then you have also ways to test dark matter. One of those is, it depends on the model of dark matter. But for instance, in the case that you have a very light, let's say axion-like dark matter, axion-like means it's not the QCD axion, but it's a particle that behaves in the Lagrangian like the axion, and is light, but different couplings and masses. So in this case, there is an effect that can be measured because this the dark matter halo has an effect on the gravitational wave signal. Then, of course, well, this doesn't require many explanations. By measuring all these binaries with high accuracy, you're performing tests of GR. And concerning something that is more cosmology, is you can do also the standard, you can use the black holes, the binary black holes, as standard candles, that in the case of gravitational waves, they are, say, standard sirens. And you can also okay, you can, this sometimes depends on the technique, requires to have an electromagnetic counterpart. And in this case, what you can do very well is to fill the Hubble diagram, so distance, velocity, distance redshift, and to measure, for instance, the local Hubble expansion, and also to perform measurements of the cosmological parameters, for instance, in lambda CDM model of cosmology. Something else that is the rest of the talk is the characterization and measurement of the stochastic gravitational wave background. Of course, I would like to stress the fact that we are measuring a new window for the first time, so there might be surprises. So it's difficult to be prepared for surprises, for the unexpected. But of course, it's important to maybe to have searches, analyses that are flexible enough that if something is different, you don't completely lose it. Okay, then the stochastic background. This slide is technical. So let me briefly say a few words, and this is this slide can be a reference later on when if you want to look at this slide. So in the case of gravitational waves, what you can do is to do the plane expansion, and here you have basically this quantity that let's focus first on this quantity when you have a point-like source. When you have a point-like source, you know that the gravitational waves are expanding, and the polarization, the plus and cross polarization, move and are orthogonal to the direction of propagation. So in the case of gravitational wave source, point-like source, like a particular binary there on the sky, you have that these indices are basically 1 and 2, because the others will be 0 due to the fact that they have to be orthogonal to the propagation direction. And then you have this quantity that is the waveform of the signal in a frequency domain. Now, in the case of the stochastic background, what you have is that this signal is coming from everywhere in the sky. So you don't have a preferred direction n, and since you don't have a preferred direction n, also these indices have to acquire an extra value, which is this number 3. So just to say technically, okay, you start having differences when you have to analyze this quantity. Second, I mean, we said that for point-like sources, you have the waveform of the binary, but in the case of the stochastic gravitational wave background, the signal is stochastic, so it's a random variable. Then random variable means superficially everything, but if you're careful, it means nothing, because when you need to do the analysis and the characterization of the background, you need exactly to measure and characterize this random variable. For many, but not all, primordial backgrounds, primordial for me means before the CMB, you have that this quantity, random variable, is Gaussian. Okay, Gaussian means it follows a Gaussian distribution. Stationary, which means that the statistical properties don't depend on time, and isotropic, the statistical properties don't depend on the particular direction at which you are pointing at. And okay, it's also unpolarized. So what I say technically is this is written here, but what I want to introduce is this quantity, because it's the quantity that will be plotted later on. This quantity is the equivalent of the energy density of dark matter, of matter, but for gravitational waves. I mean, okay, sorry. it's not exactly the same, but it has the same symbol. So here, right, this quantity that looks that one is mostly that one is actually what you have in energy. It's a frequency dependent. So it's the energy density respect to the critical density per log interval, per frequency log interval. Okay, then basically means, roughly speaking, that for a given f you have the equivalent of omega matter, but only for that frequency bin. Then why is it important to measure, or it's so exciting to measure primordial stochastic background? The reason is that we have little direct access to the primordial, to the early universe. So we know that photons are interacting to the mean path of the photons before CMB is short. This means that the source of photons in the early universe before the CMB produce photons, but today you don't detect those photons before they've scattered many times, which means that by the scattering they've lost their a lot of information about the original source. For neutrinos, we know the neutrinos here, they propagate, but the neutrinos coming from the early universe before the CMB are very weak, so it's you don't detect them. Instead, for gravitational waves, since the interaction is Planck suppressed, what you have is that a source that produces gravitational waves in the very early universe, let's say just after inflation, produce gravitational waves that don't interact with the plasma or with the structure of the universe, and this means that if you measure today gravitational waves coming from this epoch, these gravitational waves carry information of the source, and this information have not been lost by the fact that the gravitational waves could have scattered with the content of the universe. So this is why it's very important to measure. It's exciting to have a detection of the stochastic background. Roughly speaking, let's say it's the same of CMB, but at early epochs, and by means of gravitational waves. And the analogy, I guess, imagine how the CMB measurement revolutionized cosmology, and a similar thing is expected if you measure the stochastic background from in gravitational waves. So I guess that I'm running a bit late, so I want to really summarize some sources of the primordial stochastic background. By checking YouTube, I saw that, for instance, you have Blanco Pigliado speaking about strings. So, and for sure you might have other people speaking about strings, inflation, and phase transitions. So let me be quite brief. One possible source of the primordial stochastic background is cosmic strings. In some models, you have spontaneous symmetry breaking, and this spontaneous symmetry breaking leaves some objects that are topologically stable, strings, and these strings are produced, and in the universe you have many of them. They propagate at the speed of almost the speed of light. So this means that two strings can cross, and also the same string vibrate. And when two strings cross, for instance, or self-intersect, you produce rings. And these rings have, besides rings, you may have also cusp. And when since the string along the string you carry stress energy tensor, this motion of the strings implies that you have variation of the stress energy tensor, which in severe regimes implies a production of gravitational waves. So from cosmic strings, you have a network of cosmic strings, and these networks of cosmic strings produce gravitational waves. The signal, this omega gravitational waves I was mentioning before, right, for cosmic string is expected to have this kind of frequency shape. And these different lines correspond to different values of G mu, which is a parameter that is describing the energy of energy density of the strings. So you can see that there are regimes of G mu that can be probed by LISA. This is LISA, the LISA sensitivity. And there are also regimes of strings that can be detected. So some can be detected, some other can be detected. But in any case, once you perform an accurate measurement of the stochastic background, even if you're not detecting the cosmic string signal, you can put an upper bound, which is important. And then something that applies to cosmic strings, but also to other stochastic backgrounds, sources of stochastic background, is that these sources were produced in the very early universe, and they are redshifted depending on the evolution of the universe. So, for instance, I mean, this n equal to 4 is how the gravitational wave spectrum redshifts in the case of a radiation-dominated epoch. But if at some point there was a kination epoch, the spectrum is modified and you measure something like that. These are just examples. Or if you have an epoch of matter domination, instead the spectrum is deformed in this way. I mean, looking at the blue line. So
these epochs of domination are assumed to be just about Big Bang nucleosynthesis.
Much before.
Much before. So what I mean is these signals at high frequency seem to exclude, for instance, kination. Or no, let's say you can put a stronger bounds on some kind of expansion than the other. But you have to assume also when this is happening, right?
Yeah.
So this plot is made assuming that this expansion is until Big Bang nucleosynthesis, or when?
It's here. I don't remember the number. It's up to a given temperature. This one is the early universe, much before the BBN nucleosynthesis.
Okay. So it's a given temperature. Yeah, it depends on the temperature where this happens. Right?
Yeah.
Okay.
Yeah. So you can play by playing this with this temperature. You can have that the tilt starts later, for instance, here, right?
Yeah.
So what I want to advocate, I mean, this kind of detection is okay, would be wonderful, but it's hard to convert the measurement stochastic background into a very robust constraints on the evolution of the universe, because you need to be sure, for instance, that here you have only cosmic strings and you don't have something else. But from 0 to 1 you have different levels, and these levels are important, I would say, right?
Sorry, one question. I missed what these numbers mean, like n equals 6, n equals 4, and so on.
Yeah. It's how it scales with the Hubble, with the
temperature.
There's the power.
Is the temperature independence
Okay.
of the density?
Yeah, with the covolume. Yeah.
Okay.
I mean covolume. The A. Okay. In the usual expansion. Okay, then further source is inflation, and for inflation, if you are stick to a single field slow inflation, if the inflationary signal will be very small. It's flat, at least in this region, okay, and is around 10 to minus 16, 10 to minus 15 in these units. So it's below all possible, present and forthcoming experiment. This is pulsar time arrays. This region is LIGO, Einstein telescope, and this region is LISA. Okay. Of course, this you have the SIGO, but okay. Of course, if you have the SIGO, you are okay. The SIGO is not one of my, I think, one of the forthcoming experiments. Forthcoming for me means in the next 20 years. So here, this plot shows that it's hard to probe inflation. If it is, it's impossible to prove inflation if it is single field as low. But you have this kind of scenario is not the only one. For instance, one example is the axion inflation. And in axion inflation, you have a departure from the single field slow behavior. And you can see that the signal is going up at high frequency, and then you cross different experiments. So you can make, yeah.
I have a question. Can you play the same game that you did in the previous transparency also for the inflationary? So yes. If you have, for instance, an epoch of kination or some accelerated expansion, you can amplify.
Yes.
So in that case, you may have some hope to detect.
Yes. No. Yeah. What I say here, this, I mean, at quantitative level, they depend a bit from one case to the other. Okay, and one of the key points is that these things keep evolving during. It's not that you have production of gravitational waves and then it just reshifts. Here, these sources are keeping producing. But besides up to technicalities, what I'm saying here applies to any stochastic background, because it's basically how you redshift the signal once it has been produced. And this is, let's say, model source independent. Then the technicalities is how much, but okay, the idea is there. So yes, axion inflations or also as well modification of the pre-BBN epoch. Then inflation and also first order phase transitions. So I wanted to discuss.
So one question.
Yeah.
So in your previous graph, seems that some the black color was used from LIGO.
Yeah.
So does it mean that the
wait, 1 second, because I confess I'm colorblind. So you mean this one? I guess I don't see now.
Oh, I see. Is that the LIGO? Which one is the LIGO?
This one, but this is a pictorial. It's a pictorial illustration. Okay.
So they are barely ruling out or detecting some axion inflation model or something. Can you say something?
Yeah. I mean, if you want, but the lack of detection of some signal, you of the stochastic background in LIGO, you can rule out models. But again, this is really an illustrative picture in the sense that, for instance, in axion inflation, at some point, you expect that the mechanism that is pumping up the signal, the frequency stops, so it falls down. I know this, but I don't know the technicalities. So what I'm saying is that for me, the message here, the message that I wanted to convey is that it's very, what LISA can do or not do for inflation is very model dependent. And the same, and you can play in such a way with the potential, in such a way that maybe you detect the signal in LISA and not in LIGO. Maybe you can do vice versa. So you have, inflation is extremely model dependent. You have so many models, you can do many things. So yeah. So phase transition. I think that I want to discuss in detail, but no. The
I think
methods.
we have time, no?
Yeah, but I have also other slides, so this is why.
Okay.
No, I think that it's also attention of people drops down at some point. So here for first order phase transitions, let me briefly say the rationale. The rationale is that you have a definite finite temperature potential of a scalar field. In the case of the electroweak phase transition, the scalar field is the Higgs field, and you have that at very high temperature when the universe was very hot. The vacuum expectation value of the scalar field is 0, but at some point, if you have a first order phase transition, the potential evolves in such a way that at some point you start having a second minimum. And at the temperature that is called critical temperature, you have that this secondary minimum is degenerate with the one at the origin. So below this temperature, you can have that the universe or patches of the universe tunnel or perform a thermal jump from here to here. This thermal or jump or tunneling implies that in the place where the tunnel occurred, you have that the universe is in a different phase. And since these two phases are separated by a barrier, what you have that these phases are the equivalent of bubbles that due to different pressure in this phase and this phase expand. So you have bubbles that expand, and of course they carry a lot of energy density, and when they collide they also produce gravitational waves. It's not only a matter of collision, but since these bubbles expand in a plasma, they also perturb the plasma, and so you might have extra sources of gravitational waves due to these bubbles, and these different effects are called here. I mean, the collision of bubble walls, the sound waves is the coherent motion of the plasma moved by the bubbles, or turbulence when you're in the turbulence regime. There are different parameters here that are describing the phase transitions, and the signal, the stochastic background signal that results from this process is, of course, under investigation, you have development, but in first approximation, it looks like a broken power law, like that. Depending on the contribution, the bubble wall, the sound wave or turbulence, you may have that the signal at high frequency goes down with a different tilt, or instead of being a proper broken power law, is a double broken power law. Basically, you reach a peak, here you have a tilt, and then decreases at the different tilt.
What is driving the peak frequency?
Yes, the combination of everything, but the frequency or the amplitude?
The frequency that corresponds to the peak, to the...
Yeah. The point is that, I mean, alpha, okay, I try to summarize long equations, so the sense is the following. Alpha is mostly giving you the amplitude of the signal, because it's the latent heat, and it's telling you how much energy can be converted into gravitational waves. Okay? Then there is B over H. This is related to the size of the bubbles, and the size of the bubbles in the end depends on the size of bubble in the end tells you if you have many collisions or a few collisions, and also the size of the bubbles when they collide. So this is a very important quantity for the frequency of the peak. Then you have this temperature, and this temperature is the temperature at which, roughly speaking, the phase transition occurs, and this is redshifts the signal. Okay. Then this velocity, okay, again is related to in this approximated explanation is related to, again, to the amplitude of the peak. And then these coefficients are the coefficients due to the different effects: the bubble wall, the sound wave, and turbulence. Then there are different prefactors for these contributions. But okay, so I would say that in this rough explanation, the key quantities for the position of the peak is beta over h and T star. And for phase transitions at the electroweak, beta over h is a quantity that, since it's connected to the tunnel rate, it's, in summary, beta over h is a number that moves from, let's say, 1 to 1000. It's, let's say, roughly speaking, model independent. Of course, you can engineer models where you break these quantities, but in general, this is quantity. So the main driver of the frequency is also T star. So this is why I'm saying that, and people say that for electroweak phase transitions, you have that the peak is in the Lisa range.
Okay.
Yeah, but okay, everything my explanation was approximated, but I guess that the main method more or less is correct.
So this assumption that indeed in the case of the electroweak phase transition, the peak will be in the Lisa range is kind of robust, or
Yeah. Well, I can show you, I guess, in next slide. Well, okay, I guess that I have a slide about your point. The next one, I guess. So, but connected to before your question, right? So we have said we have this kind of signal, and something that is important is that in the standard model, you don't have first order phase transitions. Okay, this is and the reasons is that because in the standard model, the electroweak phase transition is a crossover and not a first order phase transition if the Higgs mass is larger than 75 GeV, which is the case. And in QCD, the same. You have that the phase transition is a crossover if you consider the universe that has not a very huge chemical potential. So I guess the important point is, in the standard model, you don't have first order phase transitions, which means that you don't have stochastic background coming from first order phase transitions. But of course, you can do BSM physics beyond the standard model physics. And of course, there are many reasons to believe that the standard model is not the complete theory. And depending on what you do, you can have you can engineer phase transitions, first order phase transitions, in the hidden sectors at high scales, not electroweak ones, okay, or at electroweak in the electroweak sector, so connected to the Higgs, to electroweak phase transition. The key point is that you need to engineer models. I'm saying engineers, but in some cases, I would say that it's even natural, the fact that you have first order phase transitions. So you can consider models where, in the case of the, in particular, and this moves to the questions, right? For the electroweak phase transitions, if you want it to be of first order, you are connected to, you need to include new radiative corrections to the electroweak sector, or to add new dynamical fields in the electroweak sector. And in order to these fields to be effective at the electroweak scale, you need that they have these new fields are at the TV scale. And of course, and now here comes the tension, right? I was saying that in principle there were models that were naturally producing first order phase transition at the electroweak scale, but then the statement was quite generic, maybe robust before LHC, and now with LHC we know that, I mean, we are measuring the electroweak sector, not very precisely, because for instance the linear coupling of the Higgs is bad measured, but still it's the situation is much before the pre-LHC epoch. So the idea is when you are doing model building and you want to modify the electroweak sector, is that, I mean, you have tools to produce the first order phase transitions, but these tools, these additional fields or methods, have drawbacks. So, for instance, if you add new color fields are very strongly, the couplings are strong, large, which means that they are very, very effective in modifying the electroweak sector. At two loops, but the phase transition, the two loop effect, since it starts involving the QCD coupling, are still very large with respect to the first one loop, but electroweak couplings. But the point is that, okay, and then you're modifying exactly what LHC is producing. So for instance, you see signals of departure from present constraints in the gluon fusion processes. Then you can have a new dynamical scalar fields, for instance, let's say an extra doublet. But when you have an extra doublet, triplet, quadruplet, whatever, you have to be careful because the mixing with the Higgs can produce, for instance, a mixing implies that all the decay rates of the Higgs are modified, right? Because you are by the mixing, you are diluting the channels of the Higgs. So you have to be careful with the Higgs signal strength. If you want new fermions, the point is that new fermions at finite temperature don't produce the typical cubic term that you need for the barrier. So it's fermions in general not very effective in producing first order phase transitions. And in general, if you want heavy fields, you have to be careful because they are Boltzmann suppressed, so they don't modify the finite temperature potential. You can play with the low energy effective effects of these fields, but okay. So these are basically ways to explore and ways to which, I mean, and things that can spoil your attempt. And now maybe the answer, right? So still you have many models that and in some parameter space regions where they produce a strong first order phase transition at the electroweak scale. You can have in SUSY scenarios, not in the MSSM, but other extension, for instance, the MSSM plus a singlet. You can have in composite models, and you can have, for instance, well, in many extensions of the standard model, but you have to play with the corners of parameter space. And one way to really extend and to be very effective is, is to add a singlet, but you have a symmetry in such a way that the singlet doesn't acquire a wave, and this saves you from many constraints. Basically, LHC cannot really prove these scenarios. You need the future colliders. Just to and Randall Sundrum scenario, warp scenario also produced this. Actually, warp scenarios can produce very strong signals. Just to in 2 seconds explain the meaning of these plots. I mean, besides the names, here, for instance, you have the kind of signal you expect for a given benchmark point of the parameter space, and and this line is the LISA sensitivity. This plot is a bit old, so the LISA sensitivity is not up to date, but the message is clear, I guess. With in SUSY as well, right? Here, this plot comes from the studies of the length of the arms, but basically we are in the region design 3. Okay, and these are different stochastic background that are expecting from first order phase transition depending on the benchmark, the benchmark in the parameter space. Here the same, this is the region detectable by LISA in the case versus alpha and the beta overage that I was mentioning before. And this one is the same, the singlet, where here you have your studying your points on the right of this line are considered detectable because these lines are represent the signal to unit ratio of the signals, which means how strong the signal is with respect to the noise. And if you want to prove the capability of LISA and the future detector, you see here in this parameter space beta overage and TR. Okay, I changed the letter, sorry, it was T star before, but again it's roughly speaking the temperature at which the phase transition happens. So you can see that from here you see that for temperatures of the letter we scale you are exactly in the LISA band. But you can see also that for high temperature, I mean, you start having synergy between LISA and Einstein telescopes or other detectors. These ones are pulsar time arrays, and these ones are ground-based detectors. Okay. Then I guess it's okay, time to conclude. So I will skip a bit of slides. I wanted to cover also some topics, but how well you can reconstruct the signals, and these ones I will have to skip due to time. But I want to highlight some problems, and these problems are very important because in the previous slides we have seen that we can have signals that are very strong, above the sensitivity of LISA, but the fact of being within the sensitivity doesn't mean that you can discover these signals. In fact, the point is that LISA is a signal-dominated experiment. Besides the stochastic background, you will have many astrophysical sources there. So in order to be able to recognize the stochastic background, you need to separate the different contributions. And for very loud events like supermassive black holes, maybe this is not a problem, but there are many signals, many events in LISA that are not very loud. This means that, and there are many, so many signals that are not very loud means that they introduce a signal noise, a confusion noise. So in order to be able to recognize the stochastic background, you need to be able to separate the stochastic background from this confusion noise due to all the sources that are there, but you are not able to resolve them individually. Moreover, you have all the problem of the instrumental noise, because the instrumental noise has also a contribution that looks like a stochastic background. So it fulfills the property that I was showing in the technical slide. And this means that, again, to recognize the stochastic background, you need to be able to separate the primordial background from the instrumental noise and all the binaries that you are not able to resolve individually. So,
Sorry, one
yeah.
quick question. You have there in one of the figures of your slide instrument noise, but I don't see it clearly. Which one is it? Which
Here?
shape?
Yes.
Yes.
Yes, instrument noise is this one.
Oh, okay.
Okay, so you are dominated by signal, by events. And this is a mock data, but okay. And here I have some slides that were explaining what I was stating about the unresolvable binaries and the noise. But so let me conclude that whenever you are able to have under control you have precise modeling of the unresolved binaries and the noise of the instrument, which is not something possible, right? Because these contributions, these in particular the noise and the binaries, some of this population will be detected individually. So statistically, you will be able to start inferring the population properties, and from the population properties you can go and have an accurate template of the unresolved binaries. So if we want to have a forecast under the assumption that we have precise templates for the noise and these instrumental for the noise and these unresolved sources, okay, you can see that Lisa will be able to detect the parameters of the phase transitions very well. Let me explain this plot, but it's just illustrative. It's a work in progress, and there are many caveats. So this is why please consider that illustrative. So here, what we are plotting is these contour lines are the errors on the percentage error on the reconstruction of beta over h, when, for instance, the signal is, for this point, as beta, the injected signal as beta over h equal to 10 and alpha 0.1. Okay, so and this plot is the same. Again, alpha, these are the injected parameters, and this is for these injected parameters how I reconstruct alpha. And you can have similar plots for the temperature and the rest. There are some degeneracies, but you have similar plots. So the main message here is that for phase transition that are sufficiently strong, so this means that you are here, for instance, you can have that the parameters of the signal and then of the phase transition process can be measured at percentage, 1% or even better accuracy. I repeat, under some assumption. Here, this assumption is important. And of course, similar conclusion applies also to cosmic strings and inflationary models. And if you have other stochastic background models of, you can repeat the analysis, and I would say I expect that the take-home message is still the same. So conclusions. The measurement of the primordial stochastic background will be a breakthrough for cosmology, particle physics, astronomy, science, as important as the first measurement of the SIMB. The stochastic background, have many primordial background, as many plausible sources, but there is no guarantee that the signal is strong enough to be detected at LISA. In any case, even if you don't detect the signal, you can impose upper bounds, and these upper bounds rules out model of cosmic strings, phase of the phase transition, inflation, and many other sources. In order to perform the correct measurement, you need to pay attention to the foregrounds, what I call the unresolvable binaries, and the noise. So this is something that is a work in progress and requires a work of the community. If such a knowledge will be achieved, LISA will be able to reconstruct the stochastic background very precisely And from the measurement of stochastic background, you can interpret the signal in terms of the parameters of your models. And since you have detected the signal very accurately, you can have a strong, very precise measurement of the parameters of the source. Of course, LISA is not only a signal and an experiment to measure stochastic background. Actually, it's an experiment designed to detect, to do astronomy. So there are mixed priorities in the collaborations and for the European Space Agency. But mixed priority means that we have to understand now things. And it's true that LISA will fly in more than 10 years. But there are many things that must be decided now. For instance, how to prioritize the mission, the science feasibility, and how, in particular, the ground segment. Ground segment means pipelines. And this must be decided in the next, let's say, 5 years. And this is very important because you are starting building the experiment now. So once you have built a piece of the experiment, if it turns out that this kills your science is killed, you don't go back. Okay? So this was the main message. So I think that LISA is in many years, but it's important to work it on now. And with that, I would conclude. Many thanks for your attention.
Okay, thank you. So we are now open to questions, please.
And I ran over time. Sorry, maybe there were questions already, but I didn't want to. It's late, right there? No, what is?
It's
6
okay.
almost.
No, it's okay. It's okay.
Okay.
So can you show a couple of transparencies before another one? No, okay, no, probably I missed. There was a plot that showed. Okay, this one. So the stochastic background and is at the level of 10 to minus 42. And for instance, galactic binaries, one or depending on the frequency, can be two orders of magnitude larger.
Mm-hmm.
So in order to have this reconstruction of 1% level, you need to subtract a signal, this population of unresolved binaries and the noise at the level of 10 to minus 2, 10 to minus 3. So
yeah, it's okay. Here, something that is maybe relevant. The loudest signals are those that are order of magnitude above the stochastic background, but they are transient signals, which means, okay, that if you go the Fourier transform, okay, also here you have something like that, right? But what I want to say is that you have a specific waveform, and the waveforms are not very degenerate. I mean, the stochastic signal and the waveform of the transient signals is not degenerate. So, and the signals that are dominated the experiment are also those that are very loud. But if they're very loud, means that the signal to noise ratio, they're very strong, and means that the measurement can be very accurate. So it's what I wanted to stress is that when we put emphasis on the precision 10 to minus 2, is a bit tricky, because it's not that you have to compare two power laws, right? I mean, and in such a way of distinguishing, you measure just the sum of the two, and in order to measure this one that is below, you need this one at 10 to the minus 2. It's a bit different because there is no much degeneracy. with the loudest. The problem is when the signals, the sources are not very loud.
So in this plot, for instance, what is the most dangerous background, let's say? What is that?
Well, I mean, yes, but this plot is impressive, but it requires a lot of, right? I would say that here, okay, I would say here, this is maybe the summary of the residuals. I split them.
Okay.
So this is the signal, the stochastic-like signal from galactic binaries. Okay, and this is the stochastic-like signal coming from extragalactic objects. So if your signal is here, your primordial signal is here, this I would say, so at this level, I would say that it's hard to detect it. Then the point is that, you know, here you are doing kind of global fit, and it's not only the amplitude of the signal matters, but also how degenerate are the signals. For instance, let's take a power law that goes like that. Okay, this is very much below these galactic binaries, right? But still, the frequency shape is so different that maybe you have the hope to distinguish them. Okay. Indeed, instead.
So I don't understand because, sorry, I don't understand this because this is all stochastic. So what you are measuring is just the convolution of the sum, right? So how do you disentangle the different contributions?
If you know the frequency shape.
Yeah, so you need a prediction. So you just do a subtraction.
No. Yeah. It was what I called in the conclusion the templates.
The templates, yeah. So you use the templates. So the question is, when you use a template and you have to subtract, you have two contributions, and the contribution that you're looking for is 2 orders of magnitude smaller than the dominant signal. Then, of course, you are subtracting a template. I don't know, you have 1000 and the template gives you 999 and you get 1. Yes, but the template has to be very precise. You understand?
Yes, indeed, there is the risk of biases. And but the point is that maybe, I mean, it's different if the 999 is everywhere or just in some regions, for instance. Because if it is everywhere, it's, I mean, because when I'm speaking about predictions, it's modeling of the signal. For instance.
So you normalize, you use some part of the spectrum that is clean, let's say, and you use this to normalize, and then you extrapolate. So anyway, it will be based on an extrapolation.
Yes, in some regions. But 1 second, because for instance, when you're measuring, for instance, let's say this signal, okay, this is it's easier to understand, right? Because it's the stellar origin black holes binaries, and it's a power law. It's from theoretical predictions. I mean, it's very hard that it is not a power law. Then this means that your analysis, you put the stellar origin black holes template, which is a power law, and you put a prior on the range. Okay, but at this level, you're not really saying the template, this is the signal. You are modeling. And then, of course, it's what we were saying before, that it's dangerous if there are mismodeling, because this introduces biases. But then, okay, then let's move the next step, right? These sources are the unresolved ones. But here, you will have detected the resolved ones. So from the resolved ones, you have information about those that you don't detect. Again, it's extrapolation, because for instance, they detect ones here of this kind of signal, the stochastic, the stellar origin black holes, will be sourced at low redshift. And here you are sensitive also to high redshift. So again, I'm saying that I fully agree that there are extrapolations, but they're very combined. So it's not just, but of course, if you want to be completely theoretical agnostic, yes, it's what you're saying is completely true.
No, and my question was just what is the level of subtraction that you need? It's 10 to minus 2, 10 to minus 3, 10 to minus 1. So just
yeah, for the noise, okay, again, it depends, right? Because I mean, these lines, these here, these conclusions were done assuming that by doing some mock data, and this mock data, what you do is you inject noise and galactic binaries and templates following a given template, and then you perform the analysis and reconstruct these plus the stochastic primordial background.
Yes, but the data that you inject, they compared to the signal, the data that you inject are at which level?
Well, here you cover everything. I mean, here you can see that you are in the region where I'm struggling converting. Okay, if I remember correctly, this corresponds to signals here of this level with the peak for the phase transitions, right? But because the peak has a particular structure. But in general, I would say that besides the templates of these signals that are worrying me, but not completely, is the prediction of the noise model. So in order to be sensitive to signals above this blue line, which is what was stated in many papers of the people, you need that the model of the noise matches the real noise at the percent level. Okay. If you are agnostic on the frequency shape of the primordial signal. If instead you just say, okay, I perform a search with a template also of the primordial signal, this is completely different because, for instance, a discrepancy in the noise here, whatever, that is, I don't know, this extra bump might be, it's not here, sorry, it's right. Imagine that this is the model of the noise, but instead the noise is the black line plus an extra bump. Okay, for if your template for the primordial signal is a power law, this inaccuracy on the noise modeling is not really affecting the primordial background detection. If instead this inaccuracy, you're looking for a bump in your primordial background, this inaccuracy becomes important. So
I think we have a question from Maurice Van Putten. Maybe you want to,
yeah,
if you
I have two.
it.
Yeah, I have two questions. One is the one I put in the chat box. I think the question here is, to what extent, first, do you believe that potentially the primordial gravitational waves are non-Gaussian? Because assuming the detector noise is primarily Gaussian, you would then have the challenge, which may be feasible, to separate non-Gaussian noise from Gaussian noise. That can actually also be done through match filtering, remarkably, which we developed, for instance, with the Beppo Sachs group from the University of Ferrara some years ago. We were able to identify signals a la Kolmogorov turbulence using match filtering in otherwise Poisson noise dominated light curves. So in that sense, I think these canonical H frequency diagrams are not directly interpretable as we would otherwise use them for identifying detectability of deterministic signals by the usual match filtering.
Mhm.
And the second question is, how sure are you that the sum of all unresolvable binaries is Gaussian? I would think it's somewhere that is also tilted towards Poisson, Poisson noise. So I'm confused about two issues then.
Yeah, okay. Thanks for the question. And in some points of this talk, I was simplifying assumption, simplifying the discussion, okay? So concerning the signal, primordial signal, in general, non-Gaussianity are possible in inflation, but the other for cosmic strings and phase transitions, you don't expect that. But of course, I mean, maybe it's here the key point, right? I'm saying that typically it's Gaussian stationary isotropic, and of course, any property that these properties are important. So, for instance, something that I didn't mention because lack of time. Also, I didn't want to go to details that it becomes messy. But the galactic binaries are in the galaxy. So this means that, for instance, the background, the confusion noise, is not isotropic, and you can perform searches that are not like the one that I was showing, but you look for anisotropies, and this helps. The point is that in order to be sensitive to the anisotropy of the signal or the polarization of the signal or non-Gaussianity of the signal, in general, the leading order contribution, which is the Gaussian, must be very strong, because LISA is, for instance, to be able to detect the anisotropy part of the signal, the isotropic part has to be very strong. So this is a suppression factor that is important. But in any case, I fully agree. And in one maybe comment, if from the theoretical point of view, it's more probable that the primordial signal is Gaussian and the noise is not Gaussian. In fact, it's true, the noise has only a contribution that is Gaussian stationary. And in particular, for instance, you have glitches, right? And glitches are not stationarity. And this is one point. And it's also not expected to be completely Gaussian. So I was, all the statistical property of the signal are very, very important. But they were going to be beyond what I was aiming at this talk. Concerning this, the foregrounds, it's so here, I can go here, and I can also tell you that yeah, I mean, it's a general argument. The galactic binaries here, right? Here what you have is that in this region, you start being in the region where the signal is dominated by a few binaries. I mean, here you go down, so this means that you have less contributions. And what I'm saying is that at high level here, the signal is expected not to be really Gaussian. It's more a Poisson. And the same, well, I'm not sure at quantitative level here. Thanks for the questions. And I think it's very good to remark that what I was discussing about the leading contribution, but any characterization of the stochasticity of the signal can be a key measurement to separate the signals.
Yeah, one naive question. In this slide that you're showing, you have the sum of all unresolvable binaries. But which data are you actually taking? Because there is no LISA data.
Because because it's coming from here, which is a work in preparation. But I mean, at qualitative, this plot is in particular for this signal tend to be precise, but if you're not really interested in details, these kind of conclusions are there in the literature in many places. Okay, for instance, this line is okay. If you want, here you have a recent study, but this line is already present in the proposal on mission 5 years ago. This line was not present there because somewhat the rate of binary merges in LIGO was maybe higher than expected, or simply people were naive and didn't think about that. So it was not in proposal, but shortly after the first detection of LIGO, people understood that there was a foreground, more or less around here. And then now it's a matter of studying the populations and trying to have a better template, a better prediction. And but maybe something else, because I mean, I don't want to make things. Here I was focusing on foregrounds that are sure, but in principle you have the stellar origin, the supermassive black holes, and the extreme mass radiation spirals. These are other sources, and really depending on the populations models, you might have that also these sources provide a confusion noise. Then the point is that, is it really Gaussian? Is popcorn noise? And I guess the tendency is to expect that even in the regime where these sources produce a relevant confusion noise, this confusion noise will be not Gaussian, will be popcorn. So pa pa pa, silence, pa pa pa. Okay? And this means that in principle it's much easier to separate the signal.
Okay, thank you very much. Well, it's a bit late, but I don't know if there is one last urgent question from the audience. No? Well, no, I think we are learning a lot. We definitely benefit. If you can send us, please, your slides so we can have
yeah, I will.
a look and then. So yeah, thank you very much for such a nice talk, and yeah, we thank you again that you woke up early to give us your talk.
Well, not so terribly early.
Okay. Germano, since at the beginning you were explaining the roadmap of LISA, you were explaining the several details, technical details. What is the price tag?
It was 12. I mean, I always lost the units because they're much more of my wallet. But it was, I guess, 12 billions possible, yes. And but now there are discussions about if it's possible to cut it a bit.
Okay.
But the numbers always escape from my mind because it's too many zeros for my life, for my personal life. Sorry, billion. Sorry, euros. Just to, yeah. I don't know. We are in Korea, the currency. Yeah.
Okay, thank you.
Okay, thank you. Then,
Okay.
Thank you again.
bye.